Hi, everyone. Good morning. My name is Kiran Kamreddy. Welcome to the Cloud-Native Databases track. I'm a product manager at CelerData, driving our clouds product strategy and product management. And today, I want to take you inside the architecture of StarRocks, specifically how we have designed it to scale, recover, and observe itself in cloud-native environments. This is not going to be a marketing pitch. I want to get into the real engineering decisions that we made as a process of building this product, the Kubernetes operator internals, the CRD architecture, the snapshot technology, all of that, which makes the database behave like a true cloud native citizen. So we'll start with why cloud-native databases are fundamentally different. Think of it like a difference between building and operating a house on a fixed foundation versus something that needs to float on water. The reason I'm trying to bring that analogy is because floating on water is something that is analogous to cloud, which is obviously moving, changing a lot. It needs to be much more flexible versus the typical rigidity and the robustness that you would find on a fixed foundation. So cloud native is more like something that needs to float on water, needs to be fluid and elastic. Then we'll go deep into StarRocks architecture itself, the deployment modes, and after that we will do three specific technical deep dives. The first one is around scaling. Second one around recovery, different kinds of failure recovery modes that we have on the product. And the third is observability, specifically going into Prometheus and Datadog. We'll also cover the strategic value of the operator as a foundation for your data lakehouse projects. And then something I want to talk about, something I'm really excited about is our AI capabilities, specifically the knowledge assistant, the vector database and vector search capabilities, and the MCP server that we have out there on our GitHub. So let's dive in. Let's get into what cloud native actually means. Cloud native means a database. Cloud native in the context of a database means it essentially needs to handle four things that traditional databases were never designed for. First and foremost is elastic scaling. For example, what I mean by that is your workload at 2 a.m. is nothing like your workload at 2 p.m. during the day or at 9 a.m. during the day when things are much more busier. So you can't have the same infrastructure or same size of the database. You don't need that size to be same at 2 a.m. versus 9 a.m. or 2 p.m. And then you can't really over provision and hope for the best. So that's where elastic scaling comes, which is your database grows and shrinks depending on what the workload you have at any point of time. And then auto recovery. This is very important because things will fail, especially when you're running anything in a computing infrastructure. Nodes will fail, availability zones will go down. And when something happens, your database cannot page someone at 3 a.m. and then wait for someone to come in and do the restore. It has to be automatic. There's no other way because if your database stops, your application stops, and your entire thing goes down. You can't just operate. So auto recovery is a fundamental capability of what makes something cloud native. And the third is deep observability. So in a dynamic environment with pod scaling up and down, you need visibility into query latency percentiles, things like resource consumption, things like the progress of the different background processes that are happening in the database, especially things like compaction. Uh, and it's not about whether the process is working or not. It's also about how effectively is that process going on? Is it going slow? Is it going fast? Or is it going according to your expected performance levels? So deep observability is a must-have capability for something that makes it cloud native. And last but not the least is cost efficiency, right? I mean, you need to be able to do all of this, but not at a very high cost. I mean, you need to be efficient with the different kinds of costs that go into standing up and running the infrastructure. Every CPU or RAM that is not being used and sitting idle is money wasted. You're paying somebody for that. So the architecture itself must enable efficient usage. So all these things really is something that I think make cloud make something really cloud native. And these are not the things that are bolt on. These are core architectural decisions that you need to make when creating an application or a database. So as I mentioned, like I'm from CelerData. We are one of the big sponsors of open source project called StarRocks. For those not familiar with StarRocks, StarRocks is a high performance MPP analytical database. Think of it as a Formula One engine for analytics. We have capabilities like StarRocks has capabilities like vectorized execution engine with a cost-based optimizer, which delivers sub-second queries on billions of rows. StarRocks uses MySQL web protocol so that all of your existing BI tools work as is. You don't have to learn a new way to interact with the database. I don't want to go deep into StarRocks because I want to talk more about what makes it cloud native. And performance is not enough in the cloud. What makes StarRocks interesting, something that I'll cover later in the talk today, is how our architecture enables all the cloud native behaviors we just discussed in the previous slide: scaling, recovery, and observability. So while we were designing and building this database, one of the critical foundational decisions that we have made that gives us a lot of power and flexibility today is this separation of compute and storage. At the top, if I go into the detail of what I mean by that, at the top, you have something called front-end nodes. These are the brain of the entire cluster. This brain is responsible for query planning, metadata management, and a lot of coordination that happens when the cluster is hit with a query. And in the middle, you see compute nodes. We also call them as CN nodes for the short term. CN stands for compute nodes. And these are the actual workhorses. They are completely stateless. That's where we get a lot of flexibility in terms of how elastic we are, because these are stateless workhorse machines. They pull data from object store, which I'll discuss later. They process it, cache what they need, and they return results to front-end nodes, which then returns the results to your application. At the bottom, it's a storage layer. It is a shared object. I mean, any shared object storage can be used. For example, AWS S3, GCS, Azure Blob, MinIO. So any durable object data layer can be plugged into the StarRocks database. So you must be thinking, why is this important, or why or how this three-layered architecture matters? The reality is that it matters a lot in cloud-native environments because of the inherent need for the compute and the storage to scale independently. For example, if you need more throughput, like if your application demands more throughput, you simply add the compute or the CN nodes. If you need more storage, object storage is something that we all know it can scale infinitely. You can independently scale your object storage without touching your CN nodes or your front-end nodes. So this is the foundation that we have at StarRocks that makes elasticity and everything else really possible. So let's talk about the Kubernetes operator itself. I'll talk high level about how the operator is structured internally. This is important because as I go on to talk more in the details, it explains why the operator is very reliable. At the beginning, you define, as you start using the operator, at the beginning, you define what you want the cluster to be via a CRD, a custom resource definition. So this is your single source of truth. You just declare what you want in terms of how many front-end nodes, how many CN nodes, what is the object storage, like where is your object storage, what kind of configuration, what kind of scaling policy. You just like declare a bunch of things. That's what is called a CRD. A CRD is something that flows into the controller of the operator, which follows the classic Kubernetes pattern: watch, compare, and reconcile. This is standard Kubernetes. And under the hood, we have something called three subcontrollers, one for each FE, CN, and BE. And each subcontroller manages its own set of Kubernetes resources, things like stateful sets, services, config maps, HPA policies, scaling policies, and service monitors. So this is the secret sauce that we bring to the table through our operator controller. And as I mentioned, the separation of concerns that were designed into the database means that the FE subcontroller can handle the leader election, while the compute subcontroller can simultaneously scale out, which means that there is no contention between these services. There is no coordination bottlenecks, as things are completely independent at the database layer, which are translated into the Kubernetes layer as well. So I talked about a little bit about the operator reconciliation loop, and this is the true heart of the operator. And this is like the 5 steps that I briefly mentioned earlier, running continuously. Watch, this is a phase where the operator is continuously watching for any changes happening to the CRD, the custom resource definition YAML file that you specify at the beginning. It will watch for any failures that are happening on the pods. It will watch for any configuration changes and other K8s Kubernetes events. And then obviously, as we have the ability to watch, then it compares against the desired state that was specified in the CRD and what is actually running on the cluster right now. And if there's a delta, it plans, the operator determines what needs to happen, scale up, roll up a pod, update a config map, or trigger a failover event. Once the plan happens, and then it acts accordingly, executes the changes, updating the stateful sets, creates HPA resources, roll out pods gracefully, and update the services. And then finally, report. It updates the status of the different changes that were made with respect to the current state, the phase, the conditions, and the component health. All of that is neatly reported and logged. So this loop runs continuously for every 15, 30 seconds. So it is as you can see, it is self-healing by design. I mean, if the watch and compare shows that something is not as per the spec, the plan and the act actually adds a pod if something is failing. So it's basically self-healing by design within the window of 10 to 15 seconds. Think of it like a thermostat for your database cluster. Thermostat is something that is like actually watching and controlling the temperature change and act accordingly in terms of turning off your heater or not, turning it on or off. Okay, that's the architectural foundation of our operator. And with that in place, let's talk a little bit about the 3 things that I originally mentioned. The first one is scaling. Let's talk about how scaling works actually in practice. So auto scaling, again, is a 4-step process built on native Kubernetes HPA. Step 1, metrics collection. It's not just CPU and memory that we watch. We also watch for concurrency, replica load, and the latency SLOs. And then there's an evaluation that happens at the HPA level, horizontal pod autoscaler level. Kubernetes compares the current metrics that are being reported against your configured thresholds. So user determines these thresholds, saying that, hey, if my CPU is beyond this threshold, or my concurrency is beyond this threshold, trigger a scaling action. So that's where the step 3 comes in. The scaling process is group aware, meaning different workload groups can scale independently. So your reporting dashboard does not steal compute or resources from your other jobs that are being running on a database, like your ingestion pipeline. So these are completely separate. And a reconciliation. This is about the stateful set replicas being updated, fast warm up, because StarRocks shares metadata efficiently. I talked about the FE architecture, which are the front ends responsible for metadata management. So because that's shared, the warm-ups are also very fast. You can also see a snapshot of a actual YAML file that kind of represents this scaling policy. Notice the behavior section there, where you, as a user, can configure stabilization windows, scaling policies to prevent flopping. And you can also set minimum replicas to 0, which means that you are actually able to like scale to 0 during non-business hours. That means you don't really have to like spend anything, like not even a cent, when you don't have to by scaling down to completely 0. So because the compute nodes are stateless, as I mentioned earlier, there is no data to move. And a new pod starts, registers with the FE, and it is serving queries within seconds. So it is that much faster compared to the traditional database systems, which involve a lot of data movement and stuff like that. Because our compute nodes are stateless by architecture, we just get started just like that within a matter of few seconds. So that's scaling. Now let's talk about failures, right? And how do we recover from failures? This is when things go wrong, because in cloud, things will go wrong for sure. For production shared data deployments, StarRocks supports an active standby disaster recovery model. In this mode, there are two clusters that run, a primary and a standby. The primary cluster handles all of your read-write traffic, and the standby maintains the FE followers that continuously sync the metadata from the primary. So by that way, the FE can become primary in the case of the original primary going down for whatever reason. So here's an interesting part. Both clusters point to the same object storage, means your actual data is not replicated to the standby cluster. So that makes the standby cluster very easy to like stand up. It doesn't cost a lot because your data is not being copied or replicated, because it's same object storage that your primary cluster is pointed to. So think of it like a two GPS systems pointing to the same warehouse. If one GPS goes down, the other already knows where everything is. So this is fundamentally different from a traditional replication-based DR, because there's no replication lag for data. Only the metadata sync needs to happen, which is orders and orders of magnitude smaller than your actual data. So that makes the whole process of maintaining disaster recovery systems on the fly with our cloud-native architectures. So this slide shows how the operator manages DR as a state machine. As I mentioned, one is the capability, the other is the actual operations or things that are involved when the DR process actually happens. This is one of the deeper engineering decisions that we made. The flow is there's a trigger, there is a to-do, there is doing, and then there is done. Which means that you trigger DR by enabling a setting to true in your YAML file. The operator, if you think about a few slides earlier, I talked about operator monitoring the cluster state. So the operator picks it up, it sets the phase to do, and then it executes the recovery logic, which means it is essentially promoting your standby FE, updating the services, reconciling resources, and the phase moves to doing. And when that is done, the phase becomes done. So you can see here on the right, where you can see the CRD status output. Every state transition is tracked with timestamps and messages. This gives you full auditability, which is pretty much critical for compliance reasons. Four design principles here are declarative, meaning everything is YAML driven. There are no manual steps involved here. There's no command line. There's nothing. There's just like one CRD file, which is YAML file that is declared at the beginning. And second is observable. Every transition is tracked. And the third principle is idempotent, meaning it is safe to retry at any phase. And the fourth one is auditable, as I just mentioned. A CRD status provides the complete compliance trail of how the disaster recovery event is moving through these different phases. So this is the technical innovation that makes a DR uniquely fast. Traditional DR systems copy data, or systems only copy pointers or metadata. The object storage, metadata snapshot, reference pointers, and the data files. There's no data file that are ever touched. I mean, you can see at the top, the orange banner says it all. There's no data copying, only metadata pointers or snapshot, and that is the reason that gives us a lot of flexibility and a lot of speed when it comes to failing over, and also a lot of consistency in terms of keeping your data safe in spite of a DR event happening. So why does this all matter? Obviously, recovery time is something that is important for anybody who has done a DR, went through a DR process or a failure process. So constant time, regardless of data volume. Restoring 1 petabyte of cluster takes the same amount of time as to restoring 1 terabyte of data, because, as I mentioned, we are only restoring metadata pointers and not moving the actual data. It's the same object storage that you originally had. The RPO is near zero because metadata sync is continuous. RTO is seconds to minutes because failover is automated. Promoting standby FE, updating kits, Kubernetes services, resume queries against the same storage. This is the kind of architectural advantage that only comes from designing. As I mentioned earlier in my presentation, the foundational design of separating compute and storage, and this is the advantage that we get because of that foundational architecture that we originally have at the database level. And let's talk about the third thing is observability, because you can't really manage something that you can't observe or measure. So our monitoring pipeline has 4 stages. StarRocks nodes exposes metrics endpoints in Prometheus format. It's pretty much standard. The operator auto creates service monitor CRDs. Prometheus scrapes the different metrics at whatever intervals that our user specifies, and use Grafana to visualize all those metrics. We expose thousands and thousands of metrics across 4 categories. Query performance, which has a bunch of metrics around latency percentiles, QPS, scan volume, and then resources, specifically CPU, memory, disk I/O per node, cluster health, which is node status, tablet replicas, compaction, and then ingestion, which is around stream load, rates, routine load lag, and transaction status, and things like that. The operator makes all of this like pretty much seamless. You don't configure Prometheus to discover StarRocks. The service monitor automatically handles it. We provide pre-built Grafana dashboards in case somebody wants to get started faster. We have pre-built. You just like upload it to your Grafana, and boom, you already have your metrics flowing into your system. And you can further customize it. Obviously, that can feed back into your HPA for scaling decisions, creating a self-managed, something like a self-managed feedback loop. For customers and teams that are using a Datadog, our integration is equally straightforward. The Datadog agent runs as a daemon set, auto-recovers, auto-discovers, startups, pods through annotations, and scrapes the same metrics endpoints. And basically, the metrics endpoint is something that is kind of like foundational, and it's pretty much can be used by any monitoring tool compatible with Prometheus. On the screen, you can see a sample configuration YAML file. It's only a few lines of code on your pod spec. It's not like, it's pretty simple to configure. So basically the key principle is it's same metrics, but same metrics that can serve multiple backends, whether you use Prometheus, Datadog, or any other open metrics compatible system. StarRocks speaks the standard. No vendor lock-in on your observability stack. So moving on here, I want to talk a little bit about CelerData. What do we do? Obviously, I've been talking about StarRocks, mentioned StarRocks database a few times, like all the time, but I work for a company called CelerData. So CelerData offers enterprise managed version of StarRocks database. StarRocks is an open source database, and we offer an enterprise managed version of the database, so customers don't have to do all heavy lifting with provisioning and managing the database on a day-to-day basis. And we provide a nice packaged version of it that customers can get started with the database like really fast and really quickly. At a high level, CelerData Cloud Services is a fully managed bring your own cloud offering. I'm stressing on bring your own cloud offering because this is a cloud offering. It's not a SaaS type of an offering. It's where, because we have seen a lot of our customers are really have concerns around security and privacy. That's why our cloud offering is more of a BYOC offering where customers bring in their AWS, Azure, GCP, or any other cloud account. And we kind of manage automate and manage the deployment and management of the database in customers' networks and VPCs in a secure, reliable, and cost-effective fashion. So, and this model helps our customers meet all of the compliance and privacy laws that they have at their end. So, CelerData Cloud gives you the power of high-performance database for real-time analytics, that is StarRocks, combined with the smarter mechanisms around scaling, monitoring, and operations, which makes the deployment and management of your real-time analytics applications much more easier and efficient. So let's zoom out a little bit here to talk high level about the operator itself. It's not just deployment tool, it is really the foundation of something that delivers your cloud native real-time data lake houses. There are three pillars of strategic value that I want to highlight. Operational codification, which is a complex MPP database operations, all of that encapsulated in an operator. You don't need deep database expertise to run a production cluster, deploy, scale, upgrade, heal. It's all in the CRD. Second is enterprise readiness, security compliance, observability, role-based access control, audit logs. All of it is built in, and business continuity. As I highlighted earlier, failures can happen in time. We deliver zero time upgrades, automated disaster recovery with point-based snapshots and near zero RPO and RTO. This is what enterprises need to trust an analytical database in production. Together, these three pillars sit on our operator foundation and enable a true cloud-native real-time data lakehouse. Now I want to shift gears a little bit to something that sets StarRocks apart in the current landscape, our AI capabilities. This isn't just a buzzword. This is AI deeply integrated into the broader database experience itself. The first thing I want to talk about is our knowledge assistant. So think of it as a co-pilot that actually understands your data model. It can generate DDL from natural language. You can say something like create a partition table for daily clickstream data, and it writes the create table statements with the right partition strategy, and then you can adjust things from there on. So it assists with DML, DDL, data loading, and data exports, like all kinds of SQL statements that you would write in the life cycle of a database. It has the ability to read your schema metadata for context-aware suggestions as well. On the right is I want to talk about our intelligent query optimization AI. It's a capability within our broader AI assistant. So this is a system which analyzes your query profiles automatically, reads the table definitions, and provides SQL level rewrite suggestions. So this is particularly important for our day-to-day users who are busy with writing a bunch of different analytical queries. They constantly have challenges with identifying how do they make the query faster, how do they adjust data modeling. So all of that now is available in an AI tool. We're calling it intelligent query optimization. It proactively identifies things like slow joins, missing indexes, data skewness before you even ask. It's like a real DBA or a SQL expert looking over your shoulder except that it never really sleeps. It's on there whenever you need it. So the key differentiator of our AI capabilities is not, this is not generic SQL assistance. It's the AI that understands your specific data model, your specific schemas, and your specific query patterns, and auto adjusts the suggestions per that. I also want to talk about beyond making the database itself smarter. StarRocks is also becoming a platform for our customers and users and enabling them to build AI applications. So what I mean by that is I want to talk about two capabilities in that context. The first is vector database. StarRocks now supports native vector indexing. You can store embeddings along your structured data, run vector similarity searches like cosine, L2, or inner product, and combine them with your standard SQL filters in a single query. So what this means is this is huge because you can now do hybrid queries, which can combine your real data with your embeddings to give you the desired results. Vector indexing and vector querying itself is huge for the RAG pipelines that you may have heard, which is used in pretty much almost all AI applications today, recommendation engines, and also the semantic search kind of use cases where vector databases and vector querying becomes very important. So you don't, with StarRocks in place, you don't really need another separate vector database. Your analytical data and embeddings live together all in one database, which is StarRocks. And the second I want to talk about is our MCP server. This is something that we are very excited about. This is our model context protocol server. This is, as you know, it's a standardized interface that lets external LMs and AI agents talk to StarRocks directly. Think of it like an API gateway specifically designed for our AI tool use patterns. Cloudy, GPT, any of your AI tool that you may be running in-house can now have access to a StarRocks database and the different kinds of tables and all of the data that exists inside the database through an MCP to get the real-time answers. Our MCP server is out there on GitHub. You can check our StarRocks GitHub repo, and you'll find the MCP server there. So the architecture flow at the bottom really tells the broader story that in terms of how we how we help our customers with their AI needs. The LLM talks to the MCP server talks to the StarRocks returns the fast analytics plus embedding results, which all of this with the core database capabilities around high concurrency, governed access, and standard protocol. So this positions StarRocks not just as an analytical database, but also an analytical backbone for your AI application ecosystem. So I know I'm running out of time here, so I quickly want to wind up by talking about the takeaways from the presentation today. Number one, cloud native is an architecture decision. It's not a bolt-on. It has to be designed from the start. And you have seen how we have included in our database architecture, which ultimately gave us a ton of benefits and advantages with how we scale, how we disaster recover, and how we do observability. Second, the Kubernetes operator codifies complex MPP operations into a declarative, self-healing control loop. Watch, compare, and reconcile. Third, our shared data architecture enables independent scaling. Pointer-based snapshots deliver constant time recovery regardless of the data volume. Four, deep observability via standard protocols means your existing monitoring stack, it just works. No special agents, no vendor lock-in. You can get all of the database metadata, all of the database monitoring data directly into your existing monitoring stack. Fifth, and not least but the least most, this is a forward-looking one. Built-in AI capabilities make StarRocks an AI-ready platform. Knowledge Assistant, Vector DB, and MCP server mean your analytical database is ready for the age of AI agents and AI applications. With that, I would like to thank you for your time. I would like to take your questions, whether operator or deployment scenarios or AI capabilities. And I'm also open for your discussion of a use case. You can reach me at kiran.comreddy@celerdata.com, You can find our documentation at docs.starrocks.io. The operator and the MCP server, all of that is open source at github.com/starrocks. Yeah, so that's about it, and we reached to the end of the presentation.